Hello everyone, welcome to Marri Reddy Institute of Technology and Management, Dundigal, Hyderabad. This is S. Kumar, working as an assistant professor for the Marri Reddy Institute of Technology and Management in the Department of EEE, Electrical and Electronics Engineering. So today I am going to explain about in the module 4 magnetic circuits. In that magnetic circuits, I am going to discuss about introduction to electromagnetic induction. So this is today topic. Let us see what is electromagnetic induction. In general, the electromagnetic induction is nothing but whenever a conductor moves in a magnetic field, EMF is induces. That means when the magnetic field linking with a conductor, the EMF is induces in that conductor. The induced EMF, the induction of EMF in a particular conductor, when the magnetic flux linking with a conductor changes, that phenomena, induction of EMF in a conductor, when the magnetic field is linking a conductor changes. So that phenomena we call it as a electromagnetic induction principle. So this electromagnetic induction principle is discovered by in 1831 a famous scientist called Michael Faraday. That's why these laws we call it as a Faraday's laws of electromagnetic induction. He demonstrated many experiments and concluded given conclusions in the form of two laws. Those two laws are called Faraday's laws. So he discovered Faraday's first law and Faraday's second law. So what are Faraday's first law and what are the Faraday's second law? Let us see on next slide. So here Faraday's laws of electromagnetic induction, as I said, in 1831 Michael Faraday, English physicist, gave the basic laws of electromagnetism. So he discovered a basic laws of electromagnetism called Faraday's laws of electromagnetic induction. So he explained, so these laws will working principle of most of the electrical motors, generators and electrical transformers and inductors and so on. So these are the working principle. Faraday's laws of electromagnetic induction, these principles are used in electric motors, generators and transformers and inductors and so on. So these are there is a relation between electric current. So this laws shows, this conclusion of these laws shows the relation between electric circuit and magnetic field. So the Faraday's laws gives the relation between electric circuit and magnetic field. So those laws we call it as a Faraday's laws of electromagnetic induction. So here what is the first law? So Faraday's first law. So Faraday's first law tells about how the EMF is induces in a particular conductor or a coil or a given coil or conductor. So it tells about how the EMF is induces in a conductor or a coil when the magnetic field is changing. Magnetic field linking with the conductor changes. So that we call it as a Faraday's first law. Here it is given a change in magnetic field of a coil of a wire will cause an EMF to induce in the coil. So that is the first law. That means that when the magnetic flux linking, so here magnetic flux linking with a coil or a conductor changes. So the linking the flux. So here the flux linkages. So flux linkages cuts the conductor. The flux linkages. So this flux linkage changes with respect to the time, then EMF is induces in that conductor is the first law. So this law, method to change the magnetic field. How the magnetic field changing, or how the flux linkages changes with a conductor or a coil. How we are brought into change in flux linkages with a conductor. So that is, these are the methods. By moving the magnet towards or away from the coil or a conductor, by moving the coil into the coil, moving the coil into or out of the magnetic field. If you are moving the coil or magnetic field linking the coil is towards the coil or away from the coil. So that way we are getting a changing flux linkages with a conductor or a coil. So another method is changing the area of a coil placed in the magnetic field. So if we are changing area, so where we are keeping the conductor in a magnetic field, so the area of magnetic field, if you are changing the area of a magnetic field in which the conductor is placed, then also we are getting a change in magnetic field linking with a coil. So by changing the area, we are changing the flux linkages. In a flux linkage with the conductor is also changes. That way we are getting induced EMF in a conductor. So by rotating the coil relative to the magnet. So if there exists a relative motion between the coil and, so coil is there, magnet is there. If you are magnetic material or magnet is there. So if you are getting a relative motion between these two, so then also we can change the flux linkages with a conductor. So these are the methods. What are they? By moving the magnet, and by moving the magnet towards the coil or away from the coil, and by moving the coil into or out of the magnetic field. Then third one is changing the area of a coil placed in the magnetic field, and by rotating the coil related to the magnet. That means there exists a relative motion between the coil and a magnet. Then also the change in flux linkages with a conductor, we will brought into the change in magnetic field, thereby the change in flux linkages cutting with the conductor, EMF is induces. So that means how does we are getting the changing flux linkages? It doesn't matter. There is a induced EMF in the conductor when flux is linking with a conductor. The flux linkages with a conductor. That is a Faraday's first law. So next one is Faraday's second law. So Faraday's second law tells about the magnitude of induced EMF in a conductor is directly proportional to rate of change of flux linkages. So that means here it states that magnitude of induced EMF in a coil is equal to rate of change of flux linkages with a coil. So that means Faraday's second law gives the magnitude of a induced EMF. It will give the magnitude of a induced EMF in a conductor. So it tells about it, or it gives the magnitude of a induced EMF in that conductor. So that is the second law. So to explain the flux linkages of a coil is nothing but, so we know that the flux linkages will gives the formula N into phi, where N is the number of turns of a coil, phi is the flux in Webers. So this is the flux linkages is given by the product of number of turns in the coil and the flux associated with that coil. So that is the flux linkages. So here we are considering a coil. So this is a coil or a loop. So we are connecting one galvanometer. Galvanometer is connected to the coil. So let us consider a coil like this. So in this magnet, so we are connecting a coil like this. For this one, there is a galvanometer is connected here. So this is the galvanometer is connected to the coil. So one permanent magnet is taken. If we are moving this permanent magnet towards the coil, there is a flux linkages. We know that the flux lines are flowing from north pole to south pole like this. So these flux lines are linking with the coil will changing by moving the magnet towards the coil and away from the coil. If you are moving the magnet, permanent magnet towards the coil, there is a deflection in a galvanometer in one direction. If you are moving the magnet away from the coil, if you are moving the permanent magnet away from the coil, the galvanometer also, there is a deflection in the galvanometer in another direction. That means the magnet is moving, permanent magnet is moving towards the coil. The galvanometer deflection is in one direction, let us say in left side direction. And if you are moving the permanent magnet away from the coil, it will give the opposite direction to the previous direction. The deflection in the galvanometer shows the opposite direction to the previous direction. That means here the permanent magnet is moving towards the coil and away from the coil. There is a movement will be taking place. Thereby the flux linking with the coil is changing. Thereby there is a deflection. We can observe the deflection in a galvanometer. So if you are moving towards a coil, the galvanometer shows in one direction of reading. If you are taking a permanent magnet away from the coil, the galvanometer is showing a reading opposite to the previous case. This way the flux is, as long as there is a movement in the permanent magnet, the direction will be produces. That means EMF is induces as long as the magnetic field is linking with a conductor. If there is no flux linking with a conductor, there is no induced EMF in the conductor. There is no induced EMF in the conductor. There is no induced current is flowing in a closed circuit or in a conductor or a coil. So that tells about Faraday's second law. So let us see. So formula for Faraday's second law. So here we are considering a magnet approaching towards a coil. In previous case, we are considering at a different instance of time, T1 and T2 we are considering. So the flux linking with the coil at T1, a time instant at T1 is N phi1. So N is the number of turns. So the number of turns of a coil is constant. At T1 instant, the flux linking with the coil is phi1. Thereby, the flux linkages with the coil at a time T1 is N phi1. Similarly, the flux linkages with the coil at a time T2. This time at instant T2, number of turns are same. The flux linkages is changes. At T2, the flux linkages with the coil is changes. At T1, the flux linkages with the coil is phi1. Whereas at T2, the flux linkages with the coil is phi2. So here the change in flux, what is the change in flux? N into phi2 minus phi1. So at T1, so this is the flux linking with the coil. At T2, the flux is linking with the coil is phi2. The total change in flux is phi2 minus phi1 is the total linkage in flux. So with the number of turns, N into phi2 minus phi1 is the total linkage of change in flux linkages with a coil at different instants T1 and T2. So similarly, let the net flux linkages with phi1 minus phi2. So change in flux is nothing but a N into this phi. This is equals N into phi2 minus phi1. So if you are taking rate of change of according to the Faraday's second law, so what is that? E is equals or EMF is equals is directly proportional to rate of change of flux linkages. Rate of change of flux linkages. So here EMF is directly proportional to N phi by T. So in next slide this is so N d phi by dt. So this is according to the Faraday's law. So EMF induced is equals N d phi by so dt. So here E is equals minus N d phi by dt, where dt negative sign in the Faraday's second law indicates the according to the Lenz law. So what is Lenz law? So Lenz law states that when an EMF is generated by changing magnetic flux, according to the Faraday's, the polarity of induced EMF is such that the current that magnetic field opposes the changing which produces heat. Here, in simply we can say that the Lenz law says that effect opposes the cause. Here, effect and cause. So here the effect is the induced EMF. Here the effect is the induced EMF. That is nothing but because of induced EMF, we can get induced current. So because of induced EMF, we are getting induced current. So this is the effect according to the Faraday's second law. So what is the cause? Flux, magnetic flux. Cause is the magnetic flux linking with a conductor. That is the cause. Because of the linking, the flux is linking with a conductor or a coil, EMF is induces. Thereby, we are getting induced current. If the circuit is closed, the current is flows. That current we call it as an induced current. So here the induced current is the effect and the magnetic flux changing with a coil or conductor is the cause. So simply the Lenz law says that induced current, that is the effect, opposes the cause. What is the cause? Change in magnetic flux linking with a coil or conductor. So Lenz law, effect opposes the cause. That's why. So here induced EMF or induced current. So that is the effect. So what is the cause? Change in magnetic flux. Rate of change of magnetic flux linking with a coil. This is. So EMF opposes the cause. So this is my negative sign used in Faraday's laws of electromagnetic induction indicates the induced EMF or change in magnetic flux opposite sign. So it is no matter whatever it is, the negative sign indicates the according to the opposing nature to the cause producing it. The EMF is the effect and cause is the change in rate of change of magnetic flux linking with a coil. So this is about second law. According to the second law, the rate of change of flux linkages is directly proportional to induced EMF. So how to find the direction of induced current or how to find the direction of induced current there is a law called Fleming's right hand rule. So according to the Fleming's right hand rule, we can determine the direction of induced current in a particular coil or a conductor. So for that one, so what is the Fleming right hand rule? If you are outstressing right hand, three fingers of a right hand, that is thumb, index finger and middle finger. If you are outstressing these three fingers perpendicular to each other, the thumb indicates the motion of a conductor and the index finger or forefinger indicates magnetic field from north pole to south pole, whereas the middle finger indicates induced current. The direction of current, induced current gives the middle finger. If you are outstressing the magnetic three fingers, that is thumb and index finger and middle finger, they are perpendicular to each other. The thumb indicates the motion of a conductor. The forefinger or index finger indicates the direction of or magnetic field from north pole to south pole, and whereas the middle finger gives the induced direction of induced current. This way we are finding the direction of induced current. So the direction of induced current can be determined by Fleming right hand rule. So next we will see how to increase EMF induced in a coil or a conductor. So we know that the formula is given by E is equals N minus N d phi by dt. So this is according to the second law. So here N is the number of turns. The first point here is by increasing the number of turns in a coil. So because EMF induced is directly proportional to number of turns. So if you are increasing the number of turns in a coil, the EMF is also increases. So this way we are increasing the EMF induced in a coil or a conductor. The second one is by increasing the magnetic field strength. Here by increasing the magnetic field strength, E is directly proportional to rate of change of flux linkages. If you are increasing the magnetic field strength, so phi by A, magnetic field. So if you are increasing magnetic field strength B, so we can increase the flux. So flux linking with a coil. Thereby we are increasing the EMF induced in a coil. The third point, the coil passes through a stronger magnetic field. If your conductor is moving in a stronger magnetic field, so thereby the magnetic lines of forces cutting with a coil is also increases. Thereby we are increasing the induced EMF in a coil. So first one is by increasing the number of turns, so we can increase the EMF induced in a coil. Second one is by increasing the magnetic field, so field strength, so we are increasing the EMF induced in a coil. Third point is, so we are moving the coil or a conductor in a strong magnetic field, the flux linkages with a coil is strong, thereby increasing the EMF. So last point here, increasing the speed of a relative motion between the coil and a magnet. So if you are increasing the speed or velocity of a conductor movement, that means the coil and a magnet, if you are moving a conductor related to the magnet, thereby we are increasing the EMF induces in a coil. This way we are increasing induced EMF in a coil. So next one is applications of a Faraday's law. As usual, we know that the basic principle applied, laws of electromagnetism. So this is the laws of electromagnetism. The Faraday's laws is used in case of electromagnetic working principle. We are using in generator, electrical generator and electrical transformers. So there we are using Faraday's laws of electromagnetic induction in transformer. That's why the Faraday laws is applicable in electrical transformer. The basic principle is also electrical generation. The electrical generators is also works on the principle of Faraday's laws of electromagnetic induction. In a special application is here you can see the induction cooker. In that also we are using Faraday's laws of electromagnetic induction. This is also works on the principle of mutual induction. There is a current flow in changes. So here when current flows to the coil, copper wire placed below the cooking container, it produces change in magnetic flux. So thereby changing the magnetic field induced in a conductive container. So that is, it is used in a induction cooker, that is works on the principle of mutual induction. So that is nothing but a Faraday's second law. Here electromagnetic flow meter. So Faraday's laws are used in electromagnetic flow meter. It is used to measure the velocity of a certain fluids. Next one is the electromagnetic theory. So in the electromagnetic theory, in order to get a Faraday's laws, Maxwell's equations, Faraday idea of lines of force is used, well known by Maxwell equations. So based on electromagnetic theory, we are using Faraday's laws in order to get a Maxwell's equations. According to the Faraday's law, change in magnetic field gives rise to change in electric field. Converse of this is used in a Maxwell's equation. Simply we can say that the Faraday's law is applicable in order to get a Maxwell equations. So we are using in electromagnetic flow meter and in order to get a Maxwell equations, and in a electrical transformer, in electrical generators and industries, and in a transformers, even telephones also we are using electromagnetic induction, Faraday's laws of electromagnetic induction. So this is all about what are the Faraday's laws, definitions for Faraday's first law and Faraday's second law. So formula for second law, and how the EMF is induces in a coil or a conductor, what are the how the flux is changing, flux linkages with a conductor is changing, how we are getting change in magnetic flux, what way we are getting change in magnetic flux, and then after what are the different types of applications by using Faraday's laws. All this is, thank you all.